Yeah, a quick recall from this slide. So we were looking at the microstructure of dual phase steels, how we get the two phase microstructure, ferrite and martensite microstructure, right. So instead of taking into fully austenitic region, we are taking the steel to a temperature where the both ferrite and austenite are coexisting. That region we known as the alpha plus gamma region or intercritical region, right, intercritical region. So the advantage of doing that intercritical heat annealing treatment is, as I already explained. So this is your eutectoid phase diagram. Suppose if your steel has 0.28% carbon, and we are taking into temperature regions where the both ferrite and austenite phases are coexisting. Suppose if you are keeping at a temperature somewhere around 800 degrees centigrade or so. So what happens here, if you are holding it here, so you form austenite with enriched amount of carbon. So let us say the amount of carbon in austenite is always higher than the ferrite, and at this temperature, even though you have a 0.2% bulk carbon concentration, your austenite carbon concentration will be slightly higher than your bulk. So doing so, we are also enriching the austenite in carbon, and subsequently if you have a microstructure containing both ferrite and austenite, the austenite with enriched in carbon, if you cool down to room temperature, and because of the increased hardenability of this austenite, so we may even form martensite at much lower cooling rates than generally you need for steels containing 0.2% carbon. That means that, so by enriching austenite in carbon, so we are also reducing the critical cooling rate required to form martensite. So subsequently, if you are cool down to this microstructure, so you have an ferrite and then austenite, which for example, and this austenite when you cool down to room temperature will transform into martensitic microstructure. So during this process, as I already explained, so you not only to have you will have a martensitic and ferritic mixture of microstructure, and when the austenite transform to martensite, you will have a volume expansion. So thus volume expansion has to be accommodated. Okay, so by means of generating mobile dislocations at the interface between the ferrite and the martensite. So these mobile dislocations are very useful to increase the ductility of the material, and the presence of martensite will also increase the strength. Okay, so that is the actual the idea behind the generating the two phase microstructure of ferrite and martensite. So increase the strength, as well as because of the mobile dislocation that are generated during this heat treatment, you would enhance the ductility of the material. Okay, so this again we to achieve this heat treatment, the critical metallurgical parameters needed are so the carbon concentration of austenite. So that is very critical, because in the factory cooling rate conditions, so we cannot really achieve high cooling rates like in a quenching heat treatment. So yeah, so with an increasing in carbon concentration of austenite, we may also have a reasonably slow cooling rate. In a reasonably slow cooling rate, you will get a martensitic microstructure, and because of the two phase mixture, so you will also have a reasonable ductility and strength, which is actually needed for the advanced high strength steels, where we have a reasonable strength and ductility. And apart from the carbon effect, so we also add other alloying elements, for example manganese, to increase the solid solution strengthening of ferrite as well as the martensite, and sometimes we also add microalloying additions, for example vanadium, niobium and titanium. And these alloying additions again they combine with carbon and nitrogen to form vanadium, niobium, titanium carbonitrides. And these precipitates are very effective to provide precipitation hardening in dual phase steels. So if the steels with strength level more than 600 MPa would invariably have some amount of precipitation hardening in it. So, the most common alloying elements that are added in dual phase steels to strengthen to increase the strength, of course with the compromise to this ductility, they are vanadium, niobium, titanium to form vanadium carbonitrates of these microalloying additions, and these three elements are commonly added to form precipitates of carbon and nitrides in austenite matrix. And the strength increases significantly based on the size and volume fraction of these precipitates. Of course, because of that ductility also decreases. But again, I mean because of the presence of a large amount of mobile dislocations during subsequent heat treatment, you would still get significant ductility in these steels. So, that is what you are seeing in the banana diagram which I showed you earlier. That yeah, the ductility is ductility of even DP 1000 can still be around 15 to 20%. Okay. So, apart from dual phase microstructure, this graph can also be used to explain the microstructure formation of trip steel. The difference between the dual phase treatment and the trip steel heat treatment is we have one extra step, what you see over here, around temperature regions of say 350 to 500 degrees centigrade. So, in this case we have an additional holding at this temperature range. So, we take it to two phase region from the room temperature, we go up to intercritical temperature regions where we form a mixture of ferrite and austenite. Okay. So, that is the same as the dual phase heat treatment, but in dual phase heat treatment we directly cool to room temperature, right. So, that the austenite whatever it is formed during this intercritical holding means holding in two phase regions, alpha plus gamma regions, and in this region again we do the enrichment of austenite in carbon as I already explained given by this phase diagram, and instead of cooling directly to room temperature as in dual phase steels, and we will be holding at intermediate temperature ranges, generally the typically temperature between 350 to 500 degrees centigrade. And what do we do in this temperature? Recall the CCT diagrams. So, when you are holding at this temperature isothermally, so the austenite is most probably will be transforming to bainite. So, because of the alloying elements what we have it, right. So, we would transform the whatever austenite that is actually forming during this intercritical treatment to bainite. Okay. And we do one trick here. So, we do not form a bainite as a classical bainite I explained in earlier classes. So, what is bainite again? So, bainite is again the mixture of ferrite and cementite in different morphology than perlite, right. So, we can have either upper bainite or lower bainite. So, upper bainite the microstructure is, so we have ferrite lath forms and the carbon subsequently migrate to the adjoining regions of this ferrite lath, and then you end up forming cementite at the interlath between, for example, the ferrite laths. So, we will have ferrite and this is cementite. So, the upper bainite microstructure typically is like this. So, now we do some trick by adding some alloying elements in order to suppress this cementite formation, this interlath cementite formation. So, this can be either interlath cementite formation in case of upper bainite, right, or it can also be the intralath cementite nucleation as in the case of a lower bainite formation. So, this is say for example lower bainite. So, now if you look at these diagrams, so I have two special alloying elements, in fact you can also include other one. So, mainly the silicon and aluminum and some extent phosphorus as well. So, this silicon aluminum is added in trip steel for very specific reason to suppress the formation of cementite. Okay. So, if the cementite is suppressed during the formation of bainite, okay, when austenite is transforming to bainite, the first is ferrite is nucleating, right. So, ferrite forms and then the carbon atoms would try to go out of the ferrite, but because of the extremely low solubility of silicon, aluminum and cementite, So, what do you mean by solubility? The cementite lattice cannot keep the silicon aluminum atoms. So, suppose imagine you have the austenitic microstructure, two-phase microstructure from the intercritical region. For example, this is austenite grain. So, if you make it bigger, so imagine this is your austenite grain, and this austenite grain is held now at temperature regions where you form bainite. Okay. So, now at this temperature what will happen? You tend to form a bainite microstructure. The austenite would transform to bainite during this holding. So, you first nucleate a ferrite lath, but this ferrite lath again you cannot have carbon, right. Carbon has to be pushed out of the ferrite to the adjoining the austenite regions. In a conventional bainite, what will happen? The moment your carbon atoms go and then they segregate, and then you would form a cementite lath in between two ferrite laths. So, now this austenite is containing more amount of silicon and aluminum, or silicon and or aluminum. Okay. So, the moment you have silicon aluminum in solid solution of austenite, the nucleation of cementite is extremely suppressed. That means that your carbon is going out, okay, but cementite cannot nucleate. Why? Because the cementite lattice cannot have a silicon and aluminum in its puissance. So, if cementite has to nucleate, then the apart from the silicon aluminum, these atoms to be pushed away, but the diffusion of silicon aluminum is extremely slow, and we end up delaying the formation of cementite at the interlath locations. So, what will happen then? Because of that, your austenite is actually getting enriched in carbon. It keeps on enriching because of the formation of ferrite during bainite formation, and these carbon atoms will try to go, and this ferrite, even if it goes, and you will try to enrich the austenite because we are suppressing the cementite formation. So, at the end of the towards the end of the transformation, the bainitic ferrite, the ferrite laths in the bainite would grow with an extreme enrichment of the carbon in untransformed austenite. Okay. So, the carbon atoms are all moving away from the bainitic ferrite, the ferrite lath in the bainite, and they are enriching the untransformed austenite considerably. And we do not nucleate cementite because the nucleation of cementite is retarded by the presence of silicon aluminum atoms in the austenite matrix. So, what will happen then now? So, you are enriching the austenite in carbon so much, you significantly reduce the MS and MF temperatures. Okay. So, the MS temperature and the MF temperature, okay, decreases by increasing in carbon concentration, right. Okay. So, what will happen now? So, you are forming the bainite without cementite. So, in principle you are forming only bainitic ferrite. Okay. So, only the ferrite laths during the bainite formation. Okay. So, only the ferrite laths during bainite formation, and you are suppressing the cementite nucleation when during this bainite transformation. So, by suppressing cementite formation, what are you doing? You are enriching the austenite, which is untransformed during this transformation, significantly in carbon, right, because if cementite is not nucleated, your untransformed austenite is getting enriched in carbon significantly, isn't it? So, now this upon sufficient enrichment, so there is also an incomplete bainite transformation because the austenite is now stabilized. Okay. So, because of the partitioning of carbon from the bainitic ferrite, and upon sufficient enrichment, the bainite transformation would not progress, and I will explain some thermodynamics in next slide, and you can now assume that upon sufficient enrichment in carbon, the austenite, which is untransformed, would remain as an austenite upon subsequent cooling, because next transformation when you cool from here, obviously Martenslik transformation. But if you are enriching austenite significantly in carbon, your MS and MF temperature would decrease much further. MF temperature would go below room temperatures, and MS would significantly reduce, there about say 250 degrees centigrade or so. So, the amount of retained austenite which is untransformed during this transformation would be retained as a retained austenite. Yes, it's clear. So, I will explain again. So, we start with a two phase intercritical microstructure which is ferrite and austenite. So, austenite is already enriched in carbon. So, this line. So, imagine the austenite is already enriched and this austenite is cooled to temperature regions where you would have an isothermal holding to form bainite. But this bainite formation is happening without the formation of cementite. Okay. How do you suppress the cementite? By adding silicon or aluminum. Okay. So, if you have a silicon aluminum, what happens? You suppress the nucleation of cementite and during the bainite formation. How you suppress the cementite formation? Because the cementite lattice, the solubility of silicon aluminum and cementite lattice is extremely low. So, if you want to nucleate cementite, then silicon and aluminum atoms should be pushed away from the nucleation sites of cementite, right. But that is not possible in kinetic terms. So, you would suppress the cementite nucleation and your bainite, the bainitic ferrite laths would start growing by pushing the carbon to the untransformed austenite. And upon sufficient enrichment of carbon in austenite, okay, and you all know that the MS temperature and MF temperature would decrease significantly. Then what will happen then? So, when you further cool from isothermal holding to room temperature, so you would end up stabilizing significant amount of retained austenite at room temperature. Okay. And this retained austenite is extremely critical, right, for the mechanical properties. So, that is what we saw in a previous slide, and this retained austenite is transforming to martensite upon loading by causing this stress induced transformation, and that lead to increasing in plasticity. Okay. So, that is why these steels are known as trip steels. So, why it's what do you mean by trip is transformation induced plasticity. So, the enhanced plasticity is induced by the transformation of austenite to martensite upon loading. Okay. And how do you stabilize the austenite? As I already explained, by suppressing cementite formation during bainite transformation. Okay. How do you suppress cementite? By adding silicon or aluminum. How do these elements suppress cementite formation? Because the solubility of silicon aluminum in cementite is very low. Okay. So, if cementite does nucleate, silicon atom or aluminum atom should be pushed out, but the diffusion rate of silicon aluminum at this temperature is very low. Okay. So, you barely move silicon aluminum atoms to nucleate cementite. So, therefore, when the bainite forms, it is just forming as a single phase as a bainitic ferrite without the nucleation of cementite, and during this process we all know that when ferrite, the solubility of carbon in ferrite is much low. So, the carbon has to go out to the untransformed austenite, is not it, and this untransformed austenite is getting enriched in carbon, and upon sufficient enrichment your MF temperature would go to below room temperature. So, subsequently when you cool down from this temperature room temperature, right, your austenite would be stabilized. Yes, it is clear. So, this is how we get a three phase microstructure. So, what are three phases in trip steel? Ferrite, which is actually formed during intercritical annealing, and then we have a bainite which is actually formed from the austenite that is formed during this intercritical annealing. Okay. But this bainite is not a conventional classical bainite. Okay. So, it is not a conventional classical bainite, you will have only a bainitic ferrite, right. So, you will have only bainitic ferrite and then some untransformed austenite during this treatment up to this point, say for example in this graph, and then subsequently when you cool back, then this austenite, some austenite may be transformed into martensite, that is very insignificant, but majority of the retained austenite which is stabilized here would be stabilized to room temperature, right. So, we will end up getting a three phase microstructure in trip steel, ferrite, okay, bainitic ferrite, right. It is not a conventional bainite, it is a bainitic ferrite plus you have a retained austenite. right. So, this is a 3-phase microstructure which is typically seen in a strip steel microstructure. So, the critical part to generate this 3-phase microstructure is this isothermal magnetic holding. So, we are doing an isothermal holding at these temperature ranges between 350 to 500 degrees centigrade to enrich the carbon, enrich austenite with carbon during this treatment, okay, so that the austenite can be retained at room temperature. Yes, it's clear. Okay, good. So, we look at in further detail about the microstructure of strip steel. So, as I already explained, the typical strip steel microstructure is shown in this figure. So, we have a ferrite which is actually stabilized during the intercritical annealing, and then so you also have the austenite that is formed during this intercritical annealing treatment, but this austenite is subsequently transformed to an isothermal magnetic microstructure during isothermal IBT, the isothermal magnetic holding, and that holding during that isothermal magnetic holding between 350 to 500 degrees centigrade, and we are transforming the austenite from the intercritical annealing to a magnetic ferrite, right. Okay. So, say for example, this was a pre-austenite grain boundary. So, it will be transforming some this austenite into a magnetic ferrite, and during this process we will push the carbon atoms to untransformed austenite, and upon sufficient enrichment of carbon the magnetic transformation ceases, and then the carbon concentration of, for example, this austenite is so high, and upon subsequent cooling to room temperature this austenite cannot transform to martensite because the MF temperature is lower than room temperature, and then this austenite is retained as a retained austenite. Okay. So, now this microstructure contains 3 phases, right. So, ferrite, you have the brown here is magnetic ferrite, which is for example magnetic ferrite, and then the white bluish islands you see over here. So, here and these are all retained austenite, you see. So, for example, in this grain, so this is our prior austenite grain boundary during intercritical annealing. Now, you see there, so we have a formation of bainite, for example, happening here, and then carbon is also getting pushed to the untransformed austenite, isn't it? And then upon sufficient enrichment, you see the stabilization of retained austenite on these regions. Okay. So, now we have a 3-phase microstructure containing ferrite, magnetic ferrite and retained austenite, right. So, we have a ferrite, magnetic ferrite and then retained austenite. Again, the trick here is the addition of silicon or aluminum. Okay. So, these two guys help us, okay, stabilizing retained austenite by suppressing cementite. Because that is very critical, right. So, cementite suppression lead to the enrichment of austenite in carbon. Upon enrichment, we reduce the MF temperature to room temperature, so that this austenite can be stabilized upon subsequent cooling after the magnetic treatment to room temperature. Okay. And the presence of retained austenite is also very critical in this microstructure. Generally, we have about say 10 to 15% of retained austenite in strip steel. And this austenite in the microstructure transforms to martensite upon loading. During this transformation, we enhance the plasticity as well as when this austenite transforms to martensite during loading, you also gain some strength and toughness advantage during this treatment. So, I like to say here as well, apart from silicon and aluminum, the modern strip steels, the modern automotive steel, they also have some amount of phosphorus. Okay. There are some inherent problem with the addition of silicon and aluminum in a large amount. Generally, in strip steel, in conventional strip steel, you can classify into 2 ways: silicon based or aluminum based strip steels. roughly, if you look at silicon based strip steels, the silicon concentration generally go up to 1.5 weight%, and in aluminum based strip steels, aluminum concentration go up not more than 1%, the maximum of 1.1 thereabout. So not more than that. There is a reason, metallurgical reason, for not adding more than 1.1 weight% aluminum that I will discuss in subsequent classes. But you can assume that there are two classification of strip steels. One is silicon based, the other one is aluminum based. And silicon based strip steels, the silicon concentration is about 1.5. Apart from that, we have manganese, which can go up to say 1.5%, and carbon typically around say 0.2%. And there are, as I already explained, there are some inherent problem with the both silicon and aluminum based strip steel, because when you have a silicon, high amount of silicon in a steel, the galvanizability is severely affected because of the oxide formation, oxalate formation, that significantly affect the adherence of the zinc coating that you give during galvanizing. So there are a lot of developments that were done to replace silicon. So one of that development is to replace silicon with aluminum. Aluminum is also very effective cementite suppressor, so it suppresses cementite as silicon does, but aluminum is very poor solid solution strengthener. Unlike silicon is a very effective ferrite solid solution strengthener. Aluminum solid solution strengthening is not as effective as silicon or manganese. So the strength gain in terms of solid solution strengthening by adding aluminum is not that significant. So we need to add other alloying elements which would increase the solid solution strengthening, as well as it should also have the cementite suppression capabilities. Okay, so for example, one such element is phosphorus. Phosphorus is very effective solid solution strengthener. Okay, and phosphorus also is known to suppress cementite formation. So we can take that advantage, and also it is not known to cause the oxide formation in steels, but phosphorus is very effective solid solution strengthener, and also it is known to suppress cementite formation. So there were some developments by adding somewhat increased amount of phosphorus in steels, so that we can increase the strength when you have aluminum based strip steels. But phosphorus is extremely notorious element during welding. Okay, so in terms of hot cracking susceptibility, phosphorus is extremely notorious. So yeah, in steel makers, they generally don't really worry about welding, but as a welding engineers, we'll have to worry about weldability as well. So you can add phosphorus to some slightly higher amount than the conventionally used, but because of this addition of phosphorus, the weldability of the material is affected extremely high. But yeah, so to generate a microstructure in a steel mill, we can increase the phosphorus to 0.005 to 0.01, that's the phosphorus range. But in strip steel, in order to make use of the effectiveness of phosphorus in suppressing cementite and increasing solid solution strengthening, the phosphorus concentration can go can be increased to, say, for example, 1.5 to 0.02. It's extremely high phosphorus. But there are some steel makers who explored the use of phosphorus to stabilize retained austenite, but then with the compromising with the compromise to weldability. Okay, so these are the common alloying elements in strip steel. We have carbon, manganese, silicon, and or aluminum, and some amount of phosphorus. Okay. So these alloying elements are extremely important to get this three-phase microstructure, as I had explained. Without these alloying elements and the heat treatment, we cannot get this multi-phase microstructure. Okay, so you need to understand that. So we need a thermal cycle, which I had explained. So and a two-stage process. We take it to intercritical annealing temperatures, and then subsequently cool to intermediate temperatures, where we keep the steels isothermally to form magnetic ferrite formation. During this process, we suppress cementite, thereby we enrich the untransformed austenite in carbon, and upon sufficient enrichment, the austenite ceases to transform to bainite, and subsequently when you cool back to room temperature, when you cool to room temperature, and because of the enrichment in carbon, the MS temperature and MS temperature decreases significantly. MF temperature goes down below room temperature, and whatever austenite it is actually untransformed during the isothermal holding is stabilized into retained austenite. Okay. So, typical mixture is we have a 10 to 15% of retained austenite. So, this is about 30% of bainite, okay, and remaining say 60 to around 60, 50 to 60% of ferrite you may have in the microstructure. Okay. And again, so imagine such a complex heat treatment and the alloying elements are needed to generate such a beautiful microstructure what we see in the slide. And with this microstructure we achieve the demanding mechanical properties that I had explained, so with high strength and ductility to make automotive components. So, now the question arises now, so we have a very high amount of alloying elements, you see phosphorus, aluminum, silicon, all of them are added to get such a beautiful microstructure. Now, when you do welding, and we cannot control the heat thermal cycle as you do it here. So, welding has one thermal cycle. Okay. So, we cannot isothermally hold it in a production process for a long time. In automotive, especially automotive industries, time is money. So, we need to now understand how these alloying elements they behave, how they segregate, how they partition, how they actually migrate during solidification and subsequent phase transformations while applying Weld thermal cycle. From that understanding, and we can develop thermal cycles that are suitable for welding these steels in trip steel and dual phase steels. To summarize, we looked at two heat treatments that are used for developing dual phase microstructure, ferritic and martensitic microstructure, and a thermal cycle, heat treatment thermal cycle used to generate a trip steel microstructure containing ferrite, carbide free bainite and retained austenite, and role of alloying elements in trip steel, for example silicon, aluminum and phosphorus, and how they suppress the cementate formation and because of suppression of cementate formation, how we enrich the austenite in carbon and to retain the some amount of austenite at room temperature.